So now we are starting with this new chapter, which is on nuclear physics. And one of the first ideas that we'll be talking about is the idea of mass energy equivalence. And you might have seen this very popular equation on the cover pages of some textbooks without really understanding why this is the case. And sorry to say, but we won't actually be understanding why this is the case in this lecture either. But we will get some idea of how to use this and what this really means. But before that, let me give you a sort of a primer on the subatomic particles that we now know. And then some things you might have learned about these, you will find out are not really true. So remember that all the masses that we talked about are measured in U, which is basically the unified atomic mass. And this is equal to 1.66 into 10 to the negative 27 kg. Not to worry, this is always going to be given in your formula sheet. And that is attached to the end of your paper. And you also probably know why we measure these in U instead of just in kgs, because the masses in itself are so small that it really doesn't make sense to measure those in kg, because we'll have a 10 to a very negative power always appearing with those. You might also know this from chemistry. So how this is defined, if I write this, so this is defined as being equal to 1/12 the mass of a carbon 12 atom. So how we use these, carbon 12 is exactly 12U, it doesn't have any decimals with it. So if we take 1/12 the mass of a carbon 12 atom, that gives us exactly 1U, and that's equal to this value. So now in terms of these, we'll be now talking about the subatomic particles that we know. So we know that we have a proton, we have a neutron, and we also have an electron. Now I know in AS we went further down into these details. So we dived down further, and we also talked about quarks and whatnot. And that's not really our focus right now. We're just talking about these big particles, you can assume. So for the proton, what you knew previously, you used to say that the relative mass of the proton and the neutron is equal, and the mass of the electron, the relative mass, is almost zero. But that is not really true if we take a very accurate measurement, and by very accurate I mean here up to 6 decimal places. So what I would find out is the mass of a proton is 1.007276 U. So this is this many atomic mass units. And your neutron, the mass of that is 1008665 U. Now subconsciously, even without knowing what I was saying, instead of unified atomic mass, I said the atomic mass unit, and that's also exactly the same thing. Some textbooks may use the atomic mass unit. Here your syllabus uses these words, unified atomic mass. And the electron has a mass of 0.000549 U. Right, so what we talked about wasn't really true, because what we did was that even to these 2 decimal places, the mass of a proton and a neutron are the same, and the mass of an electron is 0. But if we get very picky about this, then we know that the masses are not really equal of the protons and the neutrons, and similarly the mass of an electron is not 0. Then obviously your next question would be that why were we not so finicky about all of this previously, and why are we now going into these details? And just wait for a moment to actually understand what's going on here. So now these subatomic particles that we do know about, we know that these constituent particles are what make up the nucleus of an atom. So the proton and the neutron make up the nucleus, and together with the electron, this makes up the entire atom. So now that we know these masses, then it also implies that if I know these masses, I can also calculate the mass of any given atom. Let's say that for this example, we are talking about helium, just to make the calculations very straightforward. So actually, let's keep away from electrons for now. Let's say we are talking about a helium nucleus here. So I know a helium nucleus would have 2 protons and 2 neutrons. So using the masses of these, I can also calculate what the mass of the mass of a helium nucleus should be according to the masses that we've given above. So 2 protons would be 2 times this number here plus twice the mass of the neutrons because they have 2 neutrons. So when I do this calculation, the answer turns out to be 4.0318882 U. So using the same accuracy that we had for the masses of the protons and the neutrons, which was 6 dP, I also gave it to the similar accuracy here. This is what we would expect the mass of the helium nucleus to be. So this is our theoretical prediction. So this is theoretical. But what we actually found is that actually the mass of a helium nucleus is not this, it's less actually. This is 4.00150 U. Now if you are in the habit of easy answers, maybe you can attribute this difference to some significant figures or some rounding errors or something like that, but that's not true. Because this discrepancy that we find in the masses of the combined atoms and the mass of the nucleus actually, this is not just there for helium, this is something that we see with all atoms across the board. So we'll be getting to the root of this problem in a minute. First, let's just talk about what this thing really is. So first we can see there is some difference in mass. This difference in mass is called the mass defect of a nucleus. So the mass defect is defined like this. So the mass defect is the difference in mass so the difference in masses of the nucleus and the separate, basically the constituent nucleons. Right, so it's the difference in mass of all the particles together and the actual mass of the nucleus. Let's do an example to further get a hang of this. So this question says calculate the mass defect for a carbon-14 nucleus and the measured mass, so this is of the actual nucleus, is this much. So if you're talking about the nucleus, we must be also talking about the nucleons. So here you have 6 protons and 8 neutrons. So 14 minus 6, this is the total number of nucleons. 14 minus 6 gives you 8 neutrons basically. Let me also write the older values here for you, which was that the mass of a proton is 1.007276 U and the mass of a neutron is 1.008665 U. So if you want to calculate the mass of the total nucleons basically, so you have 6 protons, so 6 times this value here plus 8 neutrons, so times this value here, this is going to turn out to be 14.112976 U. So this is the mass of the constituent nucleons. It's always going to be more than the mass of the actual nucleus. So for the mass defect, what we'll be doing is just we'll be subtracting this and this mass, subtracting this from this. So let me write those here. So this minus 14.003240 U. So this turns out to be 0.1093 736 U.